Hello everyone. In the previous video we talked about numerical inverse kinematics using the Newton-Raphson method. In this video we are going to talk about another algorithm called cyclic coordinate descent, or CCD. By the way, if you hear a background music, that's the rain. So hopefully you enjoyed the nice background music of rain. So what we do in this algorithm is this. Let me show it by the example. It's way easier to convey the topic by the example. So this is what you do. If here I have this 3 degree of freedom planar arm, so here there are 3 links, right? The one in black, green, and dark blue. And here you have the target, right? This is where you want your end effector, which is here. So your end effector is here. You want this guy to go to the target location. What you do is this. You change each one of the joint variables, here theta 1, theta 2, and theta 3. You change them one at a time. You do not change them all together. You start from the very last joint and then come back to the first joint and then keep repeating it. That's why it's called cyclic. So what do I mean by that? So the question is this. If I lock the first angle and the second angle and say I'm not going to change this, all I want to change is this third angle here. What can I do to this angle? How can I change it to bring this end effector closer to the target, as close as possible, just by changing that angle only? And you say, well, that's not so hard. All I need is to connect my target point to joint number 3, the joint that I'm moving right now, the joint that I'm rotating, right? Remember, the only thing we are going to rotate about is this joint. You say connect that joint to the target by a line, and then try to rotate your third member so that it aligns with this connecting line here. Whenever they align, that is the shortest distance between your end effector and your target. So you try to, by rotating your joint 3 only, you try to make it as close as possible. Now that you're done with that, you lock an angle between 2 and 3. You lock this angle, okay? Or you lock joint 3. You're not going to change that. You're also not going to change 1. So you're only going to focus on joint number 2, which is now this one. Say, well, now this is my target joint. What can I do to this joint to bring the end effector as close as possible to the target? Again, you connect the target to joint number 2 by a line, and now you try to what? You try to bring your end effector and make it fall on this line. You did the same thing in the previous scenario too. Your end effector fell on that line. Here is the same thing, right? Here you cannot align any of these members anymore with the target, with the line connecting the target to the joint, but you can bring your end effector as close as possible by putting it on this line. That makes it the shortest distance. Correct? So again, here, this angle between joint 2 and 3, if you see, this angle here is the same as this one. And the angle of joint 1 is the same as this one. They are not changed. All you do, you are changing what? This angle, theta 2, that's all you are changing. So now your theta 2 is like this. So you're rotating your theta 2 and bringing it closer. Then, when you did your best with theta 2, now you lock your joint 3 and 2. So this angle now is going to be the same as this one. This angle here is going to be locked down. All you change is this first angle. So you say, well, if I change my first angle from here to here, I can bring it as close as possible. How? Again, I'm going to connect my target to the target joint, which is joint 1 this time, and then I'm trying to force my end effector to fall on that line. When I do that, that is the closest I can get. So you see, by changing your angles one at a time, starting from the last one to the first one, you went through one iteration of this algorithm, and you can get your end effector from way down here to what? To now here. Okay, so you see it's way closer now compared to what it was, right? Look at that distance versus this distance. So clearly you could get it closer. Now in the next iteration, you repeat the process, right? So like what? For example, I continue just one more here. So right now it is this guy here. This is my current configuration. Now go back to joint 3 again. Joint 3 is here. What can I do to this joint 3 to bring this end effector as close as possible to the target? But this angle is locked and this angle is locked. I'm not going to change them, only this guy here, theta 3. And you say, well, I connect again these two with a line, and then maybe I need to even extend it and force rotating the end effector about joint 3 to fall on that line. So if you do it, your end effector probably going to come here. So now you see, it's very, very close. It's much, much closer. And then you go to joint 2. This time you like this angle. You like this angle, and you change this one. And you rotate again, right? So you connect again, end effector to this joint. You connect with the line. You continue the line. And try to what? Rotate this so you bring the end effector here, and then you do the first one. And with several iterations of this, in most of the scenarios, you are able to get what? To get it to the target location and converge the algorithm. Okay? So this is the overall idea, and here I'll talk a little bit about the math of it. It's not really complicated math. That's the best thing of this algorithm. And it does not really depend on the derivative of any sort or Jacobian, which is a good thing and a bad thing. The good thing is it is less susceptible to being trapped, but at the same time, it takes it more iterations to converge. So here, first let me show you Matlab demos. So here I have the two members. One of them is 40 mils, the other one is 50 millimeters. And then here I have some initial angles that I have to start my algorithm with. They're like my guesses. And then I keep going as long as the error is above this tolerance, which is 10 to the negative 4, or 0.1 of a millimeter. So for members of being 40 and 50 mil, 0.1 of a mil is a tight tolerance, means you are very, very close to, this is the distance between your final location of end effector and the target. When your distance is below that, the algorithm would stop. And you also give it 1,000 iterations max to try. It's always a good idea to use a little bit more iterations for this algorithm compared to Newton-Raphson, because this is not as fast as that. But the good thing about it, as I said, is it's not susceptible too much to the initial guess, because this algorithm most of the time will converge. But again, the problem is if you make this too tight, it might not get it super tight, and it takes quite a bit of iterations to happen. So let's run this and show you some demos. So here, let's say I click on a point here and say, hey, go get there. And in this case, it was very fast, actually. Still, it is oscillating. So hopefully it can converge. You didn't see too much. I probably have to click because my initial angle is kind of matching that. So yes, it took it 69 iterations. And if you look up to 2 decimals in centimeters, or 0.1 of a mil, they are the same thing. I only have 0.1% error, and my solutions are 0.3 in radians and 5.25 in radians. Okay, so it converged, but you see 69 iterations. Now let me try a different point here. So let's say, how about here? Let's see if it can get it there. So clearly you see my initial guesses are like 18 degrees and 20 something degrees, right? And they were completely off compared to where I want the target to be. Now, did they converge? Yes. 85 iterations, it got to the angles, and the error is 0.12%, okay? Okay, let's try it one more time. I try some different locations. So now what about this? Let's see if it can stretch to there. So as long as the point I click is within that circle, which is the boundary of the workspace, ideally it should get there. And sometimes it takes it some quite bit of oscillations around the points because it cannot get it to that tight tolerance, okay? So we'll see if it ultimately will converge or not. It seems to be converging. It is doing some oscillations, and it might even get off the point again. Okay, and here I'm just showing the demo for a 2 DOF arm, not 3 DOF. But this method can easily be used for as many DOFs as you want. Okay, you see it is having a hard time getting it to that very tight tolerance. If I loosen the tolerance a little bit and make the error instead of 0.1 mil, 1 mil, right? 10 to the negative 3, not 4, then it can probably converge a lot faster. You see here, still trying its best to converge. So make sure with this method, if you go with very tight tolerance, you might not converge to the goal. You see, it is still trying, and if I stop it right now, you see I have 588 iterations. If I look at the last value of the error, does it have error? I don't think it has the keyword error, the variable error. That's this one. Let's see. You see, it is 5 times 10 to the negative 4, not 1 times 10 to the negative 4. So I got very close, but it's still not there. But as I said, if I just reduce this tolerance a little bit and loosen it up, then it has a lot better chance of converging, right? Because you easily get within those limits. You see, 23 iterations, right? Or let me try a point here, maybe. That was almost like a divergence, but now it got it, 43. Now, there is one case, I don't know if I can get it or not, you have to try several times, and the case was interesting when it tried to align the first and then the second join by rotating them and then bringing the end effector closer to the target. Something interesting happens. It's not like always it's happening. You see here, it didn't happen one time. What happened was this. So here was the target, and it was within that circle. And when it tried to get there, something like this happened. It doesn't happen too often, but something like this happened. So this one was your second member. This green one was your first member. And your target was right on this line. And then it didn't move anymore. Although my end effector is not on the target, but it did not update. You see that the robot could not move. Why? Because now the second joint and the end effector and the first joint, the line connecting them are all aligned with the line connecting them to the targets. And so when you try to rotate them to bring this end effector closer to the target, you don't need any rotation. That's the closest you can get. So your algorithm will lock here. It will not move anymore, although you have this much of distance, but it's not going to move. And again, that's when your end effector falls on the boundary of the workspace. This algorithm, there is a good chance, not always, right? So you might fall on the boundary, but here, you fall on the boundary in one of the iterations like this, you are okay, it moves. But if it happens, it doesn't happen. It's just once in so many experiments that you see something like this. But if that scenario happens, then this algorithm would fail easily. Okay, so you clearly see how nice the algorithm is working. Of course, it takes more time. It's not going to be working with super tight tolerance most of the times, or if you do it, it needs a lot of iterations. But the good thing about it, it's not as susceptible to the initial guess. You know, for Newton-Raphson, if it's off, sometimes you have a good chance of divergence or being trapped in a minimum, local minimum. While for here, right, my target is here, my initial configuration is in the first quadrant. So I make it completely off, and look what happens. So, here, you see, it can converge, right? If it's close to the initial configuration, it can converge. And if you make it completely off like this also, right, it is still what? Trying to converge, and it does. So that's the good thing about this method. No complicated math, not too much sensitivity to initial conditions, as much as you bring your expectations reasonable for the final error, okay? And be a little bit more patient. Now, let me a little bit briefly talk about the math here. As I said, it's not a complicated math. All you need is to align, as I said, the line that connects, if you look, the line that connects your joint of focus, the joint that you are focusing on, the line that connects that to the end effector should be aligned with the line that connects that joint to the target. As long as these two lines, which you can see here, one of them is the red one of them is the blue one, as long as these two, you can align them together, that's all that you need, right? That's all that you need. That's all that you need. Here it is this line, it was this line initially, this red line, and now it has to match with the blue line. Here initially it was the first one and this one, so it was this, and now you have to align it with this. So this rotation, correct? This rotation or this rotation. How do we calculate them? So we call the required angle for each joint in each step, we call it alpha I, where I is the number for the joint. Now, how do we calculate it? Let me show you that. So if you want to write the algorithm yourself, write something similar to this Matlab code that I wrote, you know how to do it. So let's say here, this is your coordinate frame in this case, and I use two DOF planar arm, but again, the formula that you get does not depend on the robot. So here is your joint number 1, this is member number 1, this is joint number 2, and this is member number 2. And also attached to it, let's say, is the end effector. This is my target point. So I can call my target point X target and Y target. And then I'm going to call my joint number 2, call it X2 and Y2. Joint number 1, I call it X1 and Y1. And the current location of the end effector, I call it X end effector and Y of end effector. As I said, let's say I'm now first focusing on joint number 1 here. Joint number 2, I'm sorry. How do I calculate the alignment angle? So as we said in the algorithm, you connect your target point to the desired joint. And then you try to what? Align the line that goes from your joint to the end effector, align this line with this line, correct? So here I define 2 unit vectors. One of them is this unit vector. One of them is this unit vector. The goal is to align these 2 unit vectors. So this one I call U1, this other one I call U2. The angle between them here, this angle is the angle I need to rotate. I call it alpha 2 because that's joint number 2. So how much is alpha 2? That's clearly the angle between U1 and U2. How can I get it? By a dot product. So if I say U1 dot U2, you know the dot product of 2 vectors is magnitude first one times magnitude second one times cosine of angle in between. So if I had this U1 dot U2 from somewhere, that gives me cosine of the angle, and then I can take a cosine inverse, and that's it. The question is, how do I calculate U1 and U2? Well, U1 is the unit vector of a line connecting your joint to what? To the end effector. So I can say U1 is what? Is x of the end effector minus x of joint 2, y of the end effector minus y of joint 2, divided by its magnitude. And what is U2? Similar, but it connects your joint 2 to the target point, so it is x of target minus x of 2 and y of target minus y of 2. And then divide this again by the magnitude of it. Done. And I have all of these numbers. The x of the end effector, x of 2, y of 2, y of the end effector, x target, y target. They all can be calculated. So U1 and U2 are completely known at each iteration. I can dot product them, and from here I can get what? Alpha 2. It is simply cosine inverse of these 2 vectors, dot producted with each other. Correct? And that's it. So it is this one, dot product with this one. Done. That gives you the angle for joint number 2. Now, if you change that 2 to I, that will give you update for any joint, right? All you need is to change that 2 to what? To arbitrary I here. So let's write it that way. Done. That's the update angle. As long as I have that formula, I'm good. Can update the angle for any of my joints. So let's put something around it, and that's all the math that you clearly need. Now, just pay attention to this important thing, that at each iteration, when you update any of the angles, what numbers in this formula have to be updated. So some numbers in this formula have to be constantly updated. Each angle that is updated, these numbers have to change. What are they? Those are the x and y of the I joint, because once one joint moves, the most of the other joints, their locations will also change. And the end effector, definitely. The end effector is the position of that is affected by all of the joints, unless one joint is just like something that simply spins at the very end. Any other thing other than the last joint that is spinning, like in a spherical wrist, will change the location of the end effector. X of target and Y of target are constant. They are just constant number given to me. So they are not updated, they are fixed. But as I said, the X, Y of the each joint and X and Y of end effector should be updated. Now question, do I need to update X and Y of every single joint when I change one angle? No. For example, here, when I modify joint number 2, the location of modify angle number 2, theta 2, the location of the first joint is not going to change. Also, the location of joint 2 itself is not going to change, right? The location of the points after joint 2 will change. So if I'm, in this case, if I'm changing theta 2 by a value of alpha 2, so basically theta 2 becomes what? Becomes theta 2 plus alpha 2, or some cases minus alpha 2, depending on whether alpha 2 is positive or not. What you need to do is look at the scenario, okay? Whether you need a positive or negative. But when you change your theta 2 like this, the location of joint 2 and joint 1 you don't need to update. But what about when you change the angle of joint 1, theta 1? When you make theta 1 to theta 1 plus or minus alpha 1, you clearly see that the location of joint 2 and the effector would change, okay? So that's something you have to keep in mind. That, let me write it down for you. As I said, I want you to have some complete algorithm. So this is the update, and then from here, each angle theta I is going to be whatever it was plus or minus alpha I. Now, I write it for you here, that when changing the angle of joint I, you need to update the locations of the end effector and any joint J where J is bigger than I. Okay, so that's the important thing. Any joint with an index bigger than the current index, their location should be updated, not all of them, because the rest of them, of course, they are not going to change. Right? So there we go. This is a little bit more complete compared to the previous one. How you change each joint and which positions would you up. And how would you change it, by the way? How would you get update? Well, of course, here you can find, when I give you the set of all angles, all of the current angles, how would you find them? Using forward kinematics, right? Forward kinematics not only give you the position of the end effector, it can also give you what? The position of any point on the robot. Okay, so if you want, I can add that as well here. The location of all A where E, joint I. You need to, I say, using the forward kinematics equations, you need to update. Good. So I guess this is a lot cleaner to say. Of course, they all come from the forward kinematics equations. Good. So the last thing before we end this video might be, and I know if I were you, I would ask, how do I know whether it's plus alpha I or negative alpha I, correct? Because that's what I said. It's either plus alpha I or negative, and that's a big thing. If I change the direction in the opposite of what it should be, my end effector is going to get further away from the target instead of getting closer. How do I know? Well, let's take a look here. So if you look at U1 and U2, clearly you see U2 has a bigger angle than U1. So I have to add, right? Well, if it was the other way around, so for example, the target was here and the line was like that, and so U2 was this vector, which had a smaller angle with respect to, let's say, x-axis compared to U1, definitely what? Definitely you had to, what? When you calculate alpha, you would definitely have to reduce. So how can I distinguish between these two cases? Well, one thing you can do is look at also the cross product of the vectors. Here, if I say what is U1 cross U2 for this scenario, you clearly see it is going to be out of the plane toward you, which indicates a positive rotation. Well, I calculated for this scenario, U1 cross U2 is going to be in the board or clockwise, which is negative. So I can say the sign that is positive alpha or negative alpha is going to be the sign of this guy here. What? U1 cross U2, okay? So if you want here, instead of saying plus or minus alpha I can write it a little bit fancier for you. And let's see if I can grab this and extend it. Hopefully, no, there we go. So I can write it like this for you. It is going to be plus the sine of U1 cross U2 times alpha I. Okay? So it's going to be cosine, and alpha I itself is, of course, what? Cosine inverse of U1 dot U2. Correct? So you can say theta I is equal to whatever it was, plus sine of U1 cross U2 times cosine inverse of U1 dot U2. Okay, and make it really nice. And U1 and U2, you know, you can calculate at any iteration. So here is what you can do, okay, with this algorithm. Okay, you know, one thing that just came to my mind, and I know, again, if I were you, I would ask, is this algorithm that I just showed to you, this CCD method, is really a good algorithm, and it looks to be working fine. But here seems to be a limitation that all of these three joints are rotary joints. What if one of them was a prismatic or two of them were prismatic joints? Could you still use this method? Could you still use this algorithm? And I want to show you that, yes, you can generalize this method to work for non-rotary joints as well, okay? So let's take a look at one scenario together for the same problem. 3 degree of freedom planar arm. And I assume the first joint is rotary, but the next two are prismatic. Okay, so I have this one, this member only rotates. It has a constant L1. And then the second member, which looks like this, and then the third member, which looks like this, these guys, they have variable length. So your L2 and your L3 can change. Okay, they are variable, and also theta 1 here is variable. Let me put a star next to them, just like the DH table. So these are the variables. So this robot is RPP, planar. If I ask it to get to a point here, say this is my target, is that possible to get there? Yes. So how can we do it? Well, let me show you a case that you have gone through one cycle, and let's say you brought your theta 1 updated, and now you want to go to L2 and L3, or backwards. If you want, I can go backwards, it's no problem. All I want to show you is what is it that I can do to shrink my or extend one of these prismatic members to get it closer. So if I bring it a little bit closer, that might be a little bit nicer. So you know what, let me bring my target here just for the sake of demonstration. See if I can demonstrate the point to you. So here, that's my target. So this is X target and Y target. And let's say at the moment, it is the time for the L2 to be updated. Okay, when L2 is updated, it means the length of L1 is not going to change. Sorry, the angle of L1 is not going to change. L1 is already fixed. And L3 is also not going to change. So all I can do is to shrink this point to bring it closer to joint number 2 or extend it further away. So basically, I can only move along this line. Right? That's the best I can do. And with that, it is going to carry this end effector parallel to whatever it is right now. To these different locations. Correct? So between all of these, which one brings this one closer to the target? And you know what? Let me move it a little bit further so you can see, because this is obvious. It's just whatever it is right now. If I bring it like here, that might make proving the point a little bit nicer and easier. So basically what it is, as you can see, I have a line and I have a point. My current location is here on this line. I can move this point on a line, and I want to know when is it that I get the closest to the targets. Okay, that's the whole thing. And you know, the closest distance will be when the line that you draw from this target point to the extension line of this member, when this guy is perpendicular, correct? So if I can bring this blue point to this current red point here, that is the closest I can bring it, right? That's the best I can do. So let's say right now, this is the previous joint. And this is the length of this member, L2. This is joint number 2, so I can call it X2 and Y2. This is joint number 3, so I can call it X3 and Y3, and I can, you know, get all of this through forward kinematics. This is your target point, so that is X target and Y target. And this is the new location of joint 3 that is closest to the target. So if you don't mind, I would call it X3 prime and Y3 prime, the new location. And the new length of this member, I would call it L2 prime. So all I need to change it is L2 prime minus L2. If I increase it by that distance, I'm getting it closer. Now the question is, how do I get it? How do I get L2 prime? And it's not so hard to do. Why? Here, if I call the unit vector going from joint 2 to joint 3, this unit vector here, if I call this guy U, or I might call it U23, and if I connect my joint 2 to the target like this, right? And if I call this vector going from point 2 to the target, this vector here, whatever you want to call, doesn't matter, just might call it vector R, for example, or you might call it U2T, going from point 2 to point T. How can I get this length, this total length of L2 prime? Well, it's obvious. L2 prime is the length of U2T times what? Times cosine of this angle. Or I can project U2T along U23, correct? That's the same thing because U23 is just what? Unit vector. So when I project that along this using dot product, the result of that is going to be L2 prime. So clear from here, L2 prime is what? It is equal to U2T dot U23. Because it's magnitude of this times magnitude of that, which is 1 times cosine of angle in between, which is exactly L2 prime. And done, that's it. And you know, U2T is what? It's the vector connecting point 2 to point 3, so that is clearly x3 minus x2, and y3 minus y2, divided by the magnitude of the vector. This whole thing dot producted by the vector that goes from 2 to t. So this is going to be xt minus x2 and yt minus y2, and then divided by the magnitude of the vector. Done. That's L2 prime, and then the distance that I need in that prismatic member, the amount of displacement, maybe you can call it D2, for example. That D2 is simply L2 prime minus L2. L2 prime is calculated, L2 is a constant, is not a constant, it's the current value of it. So the difference between them is the amount of displacement in that prismatic joint to bring it closer. Done. Yes? And if you want, you can change this to I, and then change this to what? To I plus 1, and this is to I. That's it, right? So you can, yes, you can extend this method to what? To the prismatic joints as well. There is not necessarily a limitation to have it all rotary joints. Okay, so hopefully now this method is clear to you, and I will see you in the next lecture for another method of numerical inverse kinematics. Thank you.